Okay, so state and prove the ratio test. And it's going to be that these ratios are going to be the common ratio in a geometric series, right? So 1/2 plus 1/4 plus 1/8 plus 1/16 is the Achilles catching the tortoise. This will eventually equal 1 in the sense that its partial sums will converge. But what's happening here is we're multiplying by a half, multiply by a half, multiply by a half, multiply by a half to get the next term. What that means is the ratio is 1/2. Since 1/2 is less than 1, this will actually converge to 1 over 1 minus r, which in this case is 2 because I forgot the first value. Anyway, so this is the idea. Achilles and the tortoise is this example, and we will use the ratio test to look at power series and the radius of convergence of power series. So it's just going to be everywhere. So now let's restate it. So let the sum of the C sub n's be a complex or real series. Okay. If I just said it's complex series, that includes the real numbers as well. So I didn't really need to say this. Let A sub n be a sequence defined to be equal to, well, let's make it real numbers for sure. And let's make it these ratios. The common ratio, a half, a half, a half. Then, if A sub n converges to some number L, which is less than 1, that will imply that the original series converges. In fact, it'll converge absolutely. So it's even better. We can rearrange the order of the terms. If the A sub n's, this sequence now, the sequence of ratios, converges, this sequence of ratios converges to some number that's bigger than 1, that implies that this infinite series diverges. Well, we're going to compare it to a geometric series that diverges, something like 2 plus 4 plus 8 plus 16 plus 32. That is going to diverge. Why? Because the common ratio is 2, and 2 is greater than 1. But anyway, that won't be L, but it'll be the ratio. Anyway, okay, let's see. If A sub n converges to some number L that's equal to 1, we don't know. Okay, so proof. Let A sub n converge to L that's less than 1 first. We need to show that this converges. Need prove that this series converges. Strategy. Compare to a convergent geometric series. Okay. Well, to be convergent, that means that this common ratio has to be less than 1, like 1/2 plus 1/4 plus 1/8 plus 1/16. Right? 1/2 is less than 1. Okay, that's our strategy. Now we take this and put it into a picture. This becomes a picture, or a cartoon picture. Here's 1. Here's capital L. And then all these things will be within D. And this number here will be R. And R is less than 1. Okay, here's our cartoon picture. Now, in words, since the A sub n's converge to L, which is less than, well, since I already said that L is less than 1. Since the A sub n's converge to L, we have, so then there exists an index n such that all the A sub n's are within, Well, let me just cut right to it. The a sub n's will be less than or equal to this number r, which is less than or equal to 1, which is strictly less than 1, so that we'll get a geometric series that converges for all the little n's past that capital N. And you can see this, like, I could justify this more, but you can see it in the picture. If the a sub n's are going to converge to L, they got to be in here. Okay, so they got to be less than or equal to R, where R is, L plus D. So what is R? I guess I could say let D equals 1 minus L over 2. Okay, so then actually D would be like this distance, D, and R would be like here. But whatever. And let R be L plus D. Okay. Now for this little d, we know that there exists an n such that all the a sub n's are within d. In other words, they're all in here. Okay. Well, and just to make my picture more accurate, I don't know, this doesn't look like half the distance here. Half the distance would be there, so I don't know, maybe a third of the distance. It does not matter. The only thing that matters is that r is less than 1. Okay, and you can see that in the picture. If L is strictly less than 1, then we can find an r that's strictly less than 1 with all the a sub n's in here. Okay. Okay, but then a sub n less than or equal to r, well, what is a sub n? A sub n is this ratio of real numbers. Okay, but that means that this is true. And so then what's Cn plus 2 is then less than or equal to Cn r squared. And in fact, we can take n equal to capital N just to make this very specific. And let's even just do that right at the beginning. So a sub n is less than or equal to r for all n greater than capital N. So let's actually take, let's look at C capital N plus 1 over C capital N less than or equal to R. C capital N plus 1 less than or equal to R times C capital N. And then by the same idea, C capital N plus 2 over C capital N plus 1 is less than or equal to R because of this. But then C capital N plus 2 is less than or equal to R times C capital N plus 1. But C capital N plus 1 is less than or equal to R times Cn, R squared times C capital N. And by this, we can actually get that the C capital N plus any amount are less than or equal to that number of multiples of R times the first index, C capital N. Okay. But that's great. So this will give us our comparison test. If I put these as the terms of a series and put these as the terms of a series, let's take this series where the little n is going from 1 to infinity, then this one converges since this one converges. Since this converges. Why? Well, r is less than 1. This is just some constant. It's just the size of C capital N, just that number. It's like the a. Remember we had geometric series like a times r to the n, where this is some constant, and then this would converge to a over 1 minus r when r is less than 1. Well, yeah, that's just like the a. Okay, then we're done, right? Because now this sum of the C little n's from n equals, what's the difference between these two? Just finitely many terms. This one starts later. It starts at C capital N plus 1 or something. So this one converges since it's only different. It is only different by finitely many terms in the beginning, right? Whatever, 1 through capital N minus 1 or something like that. But then this sequence converges by a previous problem where if it's absolutely convergent, that implies that it converges, and we're done. We're done with the case where L is less than 1. Okay. So we proved that if these ratios, the sequence of ratios approaches L less than 1, then this series converges. Okay, so if you're wondering if some series, you're wondering about this, some series, sum n equals 1 to infinity or 0 to infinity or whatever, and you want to know does it converge or diverge? We want to compare it to the Achilles example. These are geometric series. We know exactly when these converge or diverge, when the common ratio is less than 1. So look at the ratios here. Do the ratios of these numbers approach some number which is less than 1? Then we can compare to a geometric series and show that this converges. If it converges to some number greater than 1, what happens there? That's the next part of the proof. Maybe I'll choose a different color for this part. Now, assume that the a sub n's converge to L, which is strictly greater than 1. Then here's 1. Now here's L over here. And, the same thing will work. We have some d, which is maybe 1 minus L over 2. And then let's call this number r. R is L minus this minus d. But whatever, r is strictly greater than 1. But that means that this will diverge since r is greater than 1. This is like 2 plus 4 plus 8 plus 16 plus 32 plus dot, 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 dot. This is going to diverge because r is, in this case, 2. The common ratio is 2. 16 over 8 is 2. 8 over 4 is 2. 4 over 2 is 2. 32 over 16 is 2. So the common ratio is greater than 1. So it diverges. Okay, so now assume this. Need show that this series diverges. So we're going to compare it to a divergent geometric series. Okay, now, by this same picture, by picture and the fact that the a sub n's converge to L, which is over here, then we know that we can put all the a sub n's inside here somewhere. They're all inside there after a certain cutoff. There exists a cutoff such that all the a sub n's are greater than or equal to r. Here's r. They're all the a sub n's are in here, so they're clearly greater than or equal to r. But now again, let's just look at the Cn plus 1, Cn greater than or equal to r. That's the definition of a sub n. I just didn't want to keep writing this every time, so I gave it the name a sub n. But that implies that Cn plus 1 greater than r. And this only holds for n greater than or equal to the cutoff, for n greater than or equal to the cutoff, for n greater than or equal to the cutoff, we have Cn. And so this implies that again, now we're going to start at the cutoff and go some amount will be greater than or equal to n of those. How far we went is each time we multiply by r times the c's capital N, this cutoff Cn. Okay. So, but this is going to be a geometric series that diverges, and this one is bigger. Then, by comparison test, this sequence, whatever, 0 or 1 or whatever, diverges since it's bigger than this sequence, some constant times r to the n, which diverges since r is greater than 1, and we have a geometric series. Okay, but then this sequence diverges, but this is only different, only differs by finitely many terms. So this original sequence diverges. Because this one only has a few extra terms, finitely many, but already this one diverges. So if you add some more numbers, it's not going to make it converge, it's going to diverge again. Okay, and great. So, well, we want to show that. We want to show this. This is what we're trying to prove right now. If these common ratios go to a limit that's bigger than 1, we want to show that this diverges. Well, one way to show it diverges is show that the c sub n's don't go to 0. Okay, and actually, I guess I don't even need the comparison test for this. Yeah, I don't even need the comparison test. So let me just even get rid of all this here. So I was wrong. Well, I wasn't wrong. I mean, everything I said was true, but it was not going to help me to prove what I wanted to prove. But this is still going to help. Now, 0 is less than C capital N because why is C capital N not 0? Well, I guess we need to say that it's not 0. Let's see. Okay, with non-zero terms. Okay, so that needs to be one of the assumptions. So then we can say that this is non-zero. And so this is non-zero because r is definitely this number, which is greater than 1, so it's not 0. Less than or equal to all of these. This shows that these don't go to 0, that the Cn do not converge to 0, so the series diverges by the divergence test. And then we're actually done. Okay. That was tricky. Because if we want to prove this, like here, over here, I did actually prove that this diverges, that this absolute value sequence diverges, but that doesn't necessarily prove that this series diverges. And so this was an easier way to do that by using the divergence test. Okay. But the idea was really similar. And now we have proven this one. Well, do we have to prove this one? Well, no, it's not even making a statement. I just put it in there. It's like superfluous information. It just is reminding you that if the limit is equal to 1, we actually don't know. So, I mean, I don't need to prove that we don't know. So, yeah, now I'm done. I've proved these two. Oh, and I had to say, be a complex real series with non-zero terms. And you could probably prove the same thing by saying eventually non-zero term. I mean, what are you doing if you're just adding up a bunch of zeros? It's obviously 0. So this is not a difficult restriction. That's it. This is super important because it shows you how first of all, like, what are we doing? We're going to take any series and we can try to show if it converges or diverges by comparing to basically the Achilles and the tortoise example, where we have a geometric series that converges. right? For the same reason that we'll eventually get to where we're going, even though we have to go half of the remaining distance forever. We will get there. And what you do is this series might not be a geometric series, but what we should do is look at the ratios. And if the ratios eventually look like a geometric series, namely what these ratios between consecutive terms, if these converge to some number that's less than 1, then we basically have a geometric series in the end. Okay. That is the ratio test. Ratio.